Hello and welcome to lecture 34. In last lecture, we were discussing about the gear turbofan engine, what all are the benefits of gear turbofan engine and how we are configuring this gear turbofan engine. So, let us take what all we have discussed in last class, for which we were having configuration. It says the compressor that will be driven by HP turbine and fan will be driven by LP turbine. So, here in this case we will be solving this numerical for say calculation of thrust specific fuel consumption, thermal efficiency, propulsive efficiency, overall efficiency. These calculations are at the sea level where say flying Mach number is 0, entry temperature is 288 Kelvin and pressure is 101.325 kilopascal. Bypass ratio is 12.5, fan pressure ratio is 1.5, compressor pressure ratio is 32, engine mass flow rate or entry mass flow rate we can say it is 500 kg per second, gearbox efficiency is 99%, gear ratio is 1:3, combustion chamber efficiency is 96%, combustion pressure loss it is 3%, turbine entry temperature is 1800 Kelvin, tailpipe pressure drop is 2% and say isentropic efficiency of different components for say intake it is 90%, fan it is 90%, compressor 86%, turbine 92%, nozzle it is 96% and say the calorific value of the fuel is 45,000 kilojoule per kg. So, just try to realize these numbers what all we are discussing at this moment. Okay. So, very first we will discuss how do we solve this numerical with. So, what understanding we have. So, the information in terms of inlet or the diffuser, we have a flying Mach number that is 0, entry temperature and pressure they are given, diffuser efficiency is given. So, we can calculate what will be the velocity, what will be the temperature and exit temperature and pressure at the exit of the intake. Next component we have is fan. For this fan the efficiency and pressure ratio or compression ratio they are given. We can calculate what will be the temperature and pressure at the exit of the fan. Similarly, we have next component as our compressor. For this compressor, the compressor efficiency, overall compression ratio for this compressor is given. So, we can calculate what will be our exit pressure and temperature from this compressor. We will be having say next component, it is combustion chamber. For this combustion chamber efficiency, total pressure loss, say combustion chamber exit temperature, calorific value, those all things are given to us. So, we can calculate what will be the exit pressure from the combustion chamber and what will be the fuel air ratio. We have our component, it is HP turbine. This HP turbine basically is used to rotate the compressor. For this turbine we know what is the efficiency, we know entry temperature and based on that we can calculate what will be our exit pressure and exit temperature from the HP turbine. We have LP turbine which is used to rotate the fan. For that we have information in terms of say our turbine efficiency, we are also given with the gearbox efficiency and from that we can calculate what will be our exit pressure and temperature from the LP turbine. We have tailpipe, it is connecting our LP turbine and say turbine nozzle, in which we have loss of pressure it is given. So, we can calculate what will be the exit temperature and exit pressure from the tailpipe. We have our turbine nozzle. For this turbine nozzle we are given with say efficiency and we know we will be calculating our critical pressure ratio. Based on that we will calculate what will be our static temperature and based on that we will calculate what will be the exit velocity from this turbine nozzle. in line to that we have our fan nozzle. For that fan nozzle also we have our efficiency. For the nozzle it is given, bypass ratio is known to us, we will be calculating what will be our pressure. Based on critical pressure ratio calculation, we will calculate what will be the exit pressure, exit temperature and exit velocity. Once we have all this information, we can calculate what will be the performance parameters. Now, if you look everything, here there is one additional parameter given. It says it is having, say, gear ratio as well as gear efficiency. This gear ratio it is given, say, 1:3. Now, remember one thing, here in cycle analysis we are not discussing anything in terms of speed, though it is important parameter, but it has nothing to do in terms of our performance assessment. Okay. So, be careful about that part, why that information is given. As we go ahead, we will realize that part. So, let us try to solve this numerical here. So, this you can put in terms of your line diagram, and we will put all these stations 1, 2, 3, 4, 5, 6, 7, 8, 9, and this is my exit from the fan, and this is representing our TS diagram. So, very first thing you need to do is you make the line diagram based on the information available, and then you just try to put it on TS diagram. So, it will not give you any chances for making the mistake in terms of calculating the parameter at particular station. Okay. So, make a habit of plotting this very first. So, let us look at very first component. The first component we have is our inlet. For this inlet, m infinity is given to be 0. That means like our velocity or the flight velocity, that is what will be 0. My temperature and pressure at the entry, they are given, and we know our diffuser efficiency to be 90%. From that we can calculate what will be our exit pressure from the diffuser. So, if we will be putting this number, since my m infinity is 0, so we can say our intake exit pressure is same as our entry pressure, it is 101.325 kilopascal. Okay. Now, we will be calculating what will be our exit temperature. This exit temperature we are correlating based on isentropic relation, where my m infinity is 0. That is the reason my exit temperature will be 288 Kelvin. Okay. Since the information is given for the ground condition, so do not try to solve this for flight condition, be careful. Okay. Now, what next component we have is our fan. For this fan pressure ratio is given, it is 1.5, and fan efficiency is given 90%. So, let us look at, we know what is the entry pressure from the fan, and from that if we calculate, it says exit pressure from the fan is 151.98 kilopascal. We are correlating our pressure ratio and efficiency of the fan in order to calculate the temperature. So, it says my exit temperature from the compressor is given in terms of, say, my fan pressure ratio and fan efficiency. Let us put that number. If we are putting these numbers, then it says my exit temperature from the fan, it is 327.3 Kelvin. Okay. This will be the entry condition for my compressor, this will be the entry condition for my nozzle, fan nozzle. Okay. So, let us move towards the next component. Here in this case, the compressor ratio is given, this compressor ratio is 32. We can say based on that we will be calculating the exit pressure, it is coming 4863.6 kilopascal. Okay. In line to what all we have done for the fan calculation, our compressor efficiency and compressor compression ratio, that is what will be helping us to calculate what will be the exit temperature from this compressor. So, if we are putting these numbers, then we will get the exit temperature to be 971.17 Kelvin. Okay. So, these are the information based on which we have calculated our exit pressure and temperature for the compressor. Next component we have is our combustion chamber. It says there is a drop of 3% pressure. Here in this case, this we can say my pressure at the exit of the combustion chamber, that is it is 4717.7 kilopascal. Okay. And this is representing my mass balance. Be careful, no information it is given in terms of bleeding. So, we will not be considering that. That is what will be making our life little easy in terms of doing the calculation. But in actual engine, there may be bleeding at some location in terms of pressure and temperature. So, read the information carefully. Okay. So, let us put this as our energy balance, and we will try to write down the energy balance equation for the combustion chamber. From that, we can calculate what will be our fuel air ratio. This fuel air ratio basically is represented in terms of H05 minus H04 divided by this is my combustion chamber efficiency into calorific value of the fuel minus H05. That H05 and H04 we are writing in terms of Cp. So, be careful, for the hot gas Cp is given 1156 joule per kg, okay, a kg Kelvin. Similarly, for the air it is 1005 joule per kg Kelvin. So, let us put this number. It says my fuel air ratio is coming 0.0269. Okay. Now, since we have our turbine entry temperature, it is known to us. The next calculation it is for say exit temperature from the HP turbine. For that, we will be putting our work balance equation. So, let us put the work balance. It says what all work that will be generated or developed by HP turbine, that is what will be used to rotate our compressor. So, let us write down the equation. It says m dot core into 1 plus f Cp T05 minus T06, that is m dot core Cpc T04 minus T03. Be careful, again here nothing it is mentioned in terms of bleed. So, we will be writing this equation straight away, and from that we will calculate what will be the exit temperature from the HP turbine. Since entry turbine temperature is 1800 Kelvin, so we will get the exit temperature to be 1254.9 Kelvin. Okay. We have our turbine efficiency, that is given 94%. So, based on that we can correlate in terms of pressure ratio, or we can say in terms of expansion ratio, and if we will be putting the numbers for say temperature as well as efficiency, we can calculate what will be our exit pressure from the HP turbine, and this exit pressure is coming as 874.86 kilopascal. Okay. Similarly, let us put the formulation for LP turbine. We know this LP turbine, it is wholly been used in order to rotate only fan. Okay. So, we can write down my work balance as work developed by LP turbine, that is what will be equal to what all work required by my fan. And if we are putting this equation, it says efficiency into m dot core 1 plus f Cp T06 minus T07, and this is representing what will be my mass flow rate at the entry into Cp T03 minus T07. Be careful here in this case, now we have this efficiency, that is what will be coming into the picture. Okay. So, let us put in the formulation, and if we are putting our say gearbox efficiency to be 99%, we will get our turbine exit temperature as 801.2 Kelvin. Similarly, based on our efficiency term for the LP turbine, we can calculate what will be the exit pressure from the LP turbine, and this exit pressure if we are putting these numbers, it is coming to be 106.72 kilopascal. Okay. Now, here in this case we are given with say tailpipe information also. Suppose it is not given, just omit that part, but since this is given, it says there is 2% drop of pressure. So, if we are putting this as a number, it says my tailpipe exit pressure, it will be 104.58 kilopascal. And we know since my process is a diabatic process, and that is the reason my T08 is coming 801.2 Kelvin. Okay. Now, as we move ahead, we have our component as turbine nozzle. So, for this turbine nozzle, we will be writing down the equation for P08 by Pc, which we can say it is a critical pressure ratio. That is what is a function of nozzle efficiency and specific heat ratio. So, we have information about the specific heat ratio as 1.3 and nozzle efficiency to be 96%. If we put these numbers, then this critical pressure, it is coming to be 55.54 kilopascal. Now, we will be comparing this with our atmospheric pressure, and here in this case my critical pressure is coming lower than the atmospheric pressure. That means, my nozzle is unchoked nozzle and exit pressure P9, that is what will be equal to atmospheric pressure, that is 101.325 kilopascal. Okay. Once we have this static pressure known to us, our next requirement is to calculate what will be the static temperature. So, static temperature we can calculate based on our temperature ratio. So, here in this case, if we are calculating the exit static temperature, then it is coming 795.37 Kelvin. Okay. Now, we have a formula for the exit velocity, that is 2 Cp into nozzle efficiency T08 minus T9. So, if we will be putting these numbers, my exit velocity is coming to be 113.7 meter per second. So, this will be the exit velocity from the turbine nozzle. Okay. Same way we can do our calculation for the say fan nozzle. This fan nozzle we are representing from process 3 to 10. So, we can write down our critical pressure ratio as P03 by Pc. Here in this case, we are having this to be the nozzle efficiency of the fan and specific heat, that is 1.4. If we are writing the formulation for that, and if we calculate our critical pressure, that is coming to be 77.975 kilopascal. So, here in this case, when we are comparing, it says this pressure is lower than that of the atmospheric pressure, and that is the reason why my nozzle is unchoked nozzle, and because of that we can say my exit pressure from the fan nozzle will be the atmospheric pressure, it is 101.325 kilopascal. Okay, means here in this case, for this numerical, both the nozzles are unchoked nozzle. So, you need to do this calculation very carefully. Okay. Now, let us move towards the calculation for the static temperature at the exit from the fan nozzle. We are writing that in terms of the temperature ratio, and if we are calculating the fan exit static temperature, it is coming 291.5 Kelvin. We have our formula for the velocity calculation, and here let me put the point, say this Cp value what we are putting, be careful, put that in joules, joule per kg Kelvin, otherwise you will not be getting this velocity. It is a, be careful about this part. Okay. So, if we are putting this as a number, the exit velocity from the fan nozzle is coming to be 262.84 meter per second. Okay. Now, since these two velocities are known to us, our requirement is to do calculation for the thrust, and for that thrust calculation we have our pressure thrust term, where we are looking for what will be the area. So, area of fan nozzle, area of turbine nozzle, that need to be calculated. So, let us put this as a part. Suppose if we consider we have our bypass ratio, this information is known to us. So, bypass ratio we are writing in terms of cold air by hot air, we can say it is m dot fan by m dot core. My total mass flow rate we can write down as 1 plus beta into m dot core. So, we do not have any information about the core mass flow rate. What mass flow rate is given to us, that is total mass flow rate, that is 500 kg per second. So, be careful about what information is given to us. So, total mass flow rate or engine mass flow rate is given, that means it is 500 kg per second. We have our bypass ratio of 12.5. If we are putting this number, the core mass flow rate is coming to be 37.04 kg per second. Okay. Now, if we will put this as a ratio, this will give the fan mass flow rate, it is 462.96 kg per second. Now, both the mass flow rates are known to us. So, that is where we will be using our continuity equation. Say for the turbine nozzle, we can write down my m dot core or m dot 9, it is say density into area into velocity. This m dot 9 we are writing in terms of m dot core into bracket 1 plus f into V 9 into density. This density we can calculate based on static temperature and static pressure. Since my static pressure at the exit is atmospheric pressure, so we will be putting this in terms of Pascal. Same way, this is 287, and if we will do the calculation, my density is coming to be 0.44 kg per meter cube. And once this density is known to us, we can calculate our exit area. This area is coming 0.7534 meter square. Okay. Same way you can do your calculation for the fan. What will be the change? My mass flow rate will be m dot fan. So, let us put this, it says it is m dot fan, that is density into area into velocity. M dot fan, it is known to us, this rho 10 it is unknown. So, this density at the exit we can calculate P 10 by R T 10. This pressure is atmospheric pressure. Static temperature also we have calculated, it gives the density to be 1.21 kg per meter cube. And if we will write this in the area equation, my area will be coming as 1.454 meter square. Okay. So, the formulation you need to be very careful in terms of which flow rate, which mass flow rate you are talking about. Do not commit mistake here, specifically when we are discussing about the turbofan engine. Okay. Now, the next it is to calculate our performance parameters. This performance parameter, very first we will be calculating, that is our thrust. That thrust we are writing in this equation, this m dot fan V 10 minus V infinity, A 10 P 10 minus P infinity, plus this is for the hot section, it is m dot core 1 plus f V 9 minus V infinity plus A 9 P 9 minus P infinity. All these numbers are known to us. We know our V infinity is 0. That is the reason my net thrust is coming 126.01 kilonewton. Okay. Now, the next component we have is a thrust specific fuel consumption. This thrust specific fuel consumption we are writing in terms of F into m dot core divided by thrust. These numbers are known to us. We know F is 0.0269, my core mass flow rate is 37.04, and thrust we have calculated, that is giving me say thrust specific fuel consumption to be 7.9 gram per kilonewton second. Okay. Now, we will be doing our calculation for the propulsive efficiency. In this propulsive efficiency, it is a function of my flight velocity. This flight velocity we have is 0, that means propulsive efficiency is 0. We can do our calculation for the thermal efficiency. For this thermal efficiency, the term it is say V infinity, that is coming to be 0. So, if we will do this calculation, that is what will be giving the thermal efficiency to be 36.2%. Okay. So, this is how we are doing our calculation for propulsive and thermal efficiency. Since my propulsive efficiency is 0, that means my overall efficiency also will be 0. Okay. So, let us come to the point here. It says we have done this numerical for the ground condition, where temperature and pressure they are known to us. We have done our calculation for the exit area of the fan nozzle as well as for the core engine or the turbine nozzle. The net thrust developed by this engine is 126 kilonewton. Thrust specific fuel consumption also we have calculated, and our propulsive efficiency is 0 because it is a ground condition. Thermal efficiency is coming 36.2% and overall efficiency, that is 0. Okay. So, now here we are stopping with this calculation. In next lecture we will be discussing about the performance parameter. Okay. What all will be the effect of the cycle parameters on the performance of the engine, and we will try to realize how people they are moving towards the selection of different numbers. Okay. So, here we are stopping with. Thank you very much.